Successful setup, which is called the Standard Model, which has a bunch of matter particles, quarks and leptons, and all of these interaction bosons, as we call them. And we got there through multiple ways. In the early days, we used accelerators, but in the very early days, we used natural accelerators, which are basically cosmic accelerators. So the way particle physics started is that people would send up a balloon into the upper atmosphere, and under that balloon there was a can with basically nuclear emulsion. Nuclear emulsion is a kind of a photographic emulsion, but it's super slow stuff. But you can think of it as photographic film. And you can put on cloud chambers on the ground, that people also did. And then, of course, these were the early days, and we didn't know all that much, so you got a discovery every week. So that was a good time to be a physicist. And for example, we predicted the existence of the pion, but instead of that saw the muon. Now, it's still true that the highest energy cosmic rays are well beyond the reach of current accelerators, and that's why people do experiments in the ice in Antarctica and things like that, where you can look at these very high energy particles. To give you an idea of what a photographic nuclear emulsion looks like, this is one after it was developed. There's actually a beautiful song. So to give you an idea, this is about the width of a hair. This is the width of a hair. And what you see here is actually a neutrino that came in and hit a nucleus. And those black lines that you see are nuclear fragments that are drifting, or that are expelled to the side of the interaction. Okay? And a point here is about a micron width, so it's about 1/100th of a hair thickness. Emulsion is a beautiful detector, except that it's a pain to work with. This is an experiment that was done in the 90s, and to do that experiment you had to scan 10 to the 13 fields like this, so it was a bit of work. So then came the accelerators, so far so good. The first lab accelerators appeared in the 1940s, and then what happened is that we discovered these many new strongly interacting particles, and that's how the whole quark model came up, and people postulated the existence of quarks. There was a big debate, by the way, whether quarks were just a useful mathematical tool, or whether they are actual particles or not. It turned out these things are actually particles, and this is how we ended up with the quark model and probing everything, and we learned an enormous amount out of all of that. I should say that cyclotrons, which in terms of particle physics are tools of the past, are still very much tools of the present and of the future. They play a key role in medical imaging nowadays, in cancer treatment through proton therapy and things like that, and they may have a very bright future in solving our energy problems. There's something called the energy amplifier, which relies on cyclotrons. They haven't evolved all that much, though. I found this picture, I think, even on the Nevis website. This is a picture of the downtown Columbia cyclotron around 1940. This is a picture of a modern cyclotron. This is one used for, in a hospital for cancer treatment. Basically, these devices really did not change all that much. From there, we went to bigger and bigger and bigger. So we had a cyclotron, so this is about man size, and then you have accelerators. This one is under construction, but you can see you can walk around this thing in probably about a minute. This is the Large Hadron Collider in Geneva. It would take about a day to walk around this at a sustained pace. Here it is, superimposed on the map, and this is the landing strip at the Geneva airport, so it gives you an idea of the size of the thing. So why are we doing this? Why are we going bigger and bigger? And this comes back to the problem of light. The point is the following. If you want to look at stuff, we use light. So that's a good thing. But to be able to see an object, the wavelength of that light has to be smaller than the object. Okay? And you can intuitively understand that, right? Suppose you have a tiny, tiny little object and you have a wavelength that is like this, then that light just does not have the resolving power to see that object. Okay? And the intuitive image is completely right there. And so maybe you asked yourself, you know, in high school when you were put in front of a microscope and you got to see a cell, you would think, okay, but why can't I now see a molecule through this thing, right? I mean, they tell me there are molecules, why not? And it turns out that visible light has a wavelength that allows you to see cells, right? But it doesn't allow you to see anything smaller, really. And to go to smaller and smaller wavelengths, which is here, there's a direct mapping to energy of that light, and that energy goes up and up and up to go to smaller and smaller wavelengths. So if you want to look at objects that are smaller and smaller and smaller, and look inside objects that are small, you need to go to higher and higher energies. And this is why we build these big accelerators, and that allows us to go and explore this region where you have molecules and atoms and nuclei and even smaller than that. Okay? So far, so good? Okay, so we built this huge thing which is called the Large Hadron Collider, and we put huge detectors around this, and this is really what we have that allows us to probe at the deepest of matter at this point. And this is getting me close to the end of the first part of my talk, the one where we have been discussing all the tools at our disposal. And I'm sure there were talks on this as well. So this is big, right? Here's a person, so there we are. And so this thing is quite